In this tutorial, we're going to be covering an extension to the Introduction to Classes, building a mesh crawler that can navigate across a mesh geometry. This is going to be what the output looks like, so trails drawn on a 3D geometry. If you want to start by opening up the example file, you can, but I'm going to hide this for now. And actually the first thing that we want to look at is how to go from a polysurface to a mesh inside of Rhino. So anyone that has Rhino 7, this is quite easy now. Before this, it was very difficult to nicely go from a polysurface to a mesh. Now though, Rhino has an option to select a polysurface, type quad remesh, and then it gives us some options here. We can just hit OK, and this will actually give us a nicely retopologized mesh. So we have this mesh here. I'm going to just change that layer so we can hide our polysurface. We have a remeshed version of that polysurface. It tries to preserve hard edges where it reads them, or creases, so fairly close to our polysurface, and we can adjust those settings if we need it to be closer, but for this example, this is going to be fine. Okay, so we can go ahead and get into Grasshopper and Python. So you can see in this structure that it's a fairly simple setup, at least inside of Grasshopper. So we have one component that is a GH Python component, and we have both a trail and a mesh output. So we're actually going to render certain geometric properties onto the mesh, but that's just for visualization. And the actual output is going to be trails drawn on this mesh. And then the input is just an input mesh, which is going to be this mesh here, and a set of points. Now you can either draw these on like I've done here, or you could double click and type populate geometry, plug our mesh into the geometry input, and this is just going to populate points on the surface of the mesh. So this is an option, or you can just right click, set multiple points, and just click on your mesh. Okay, now we're going to get started from scratch. So double click and type GH Python script. I'm going to rename this mesh crawler. We know our outputs, but I'll come back to those in a second. One thing that we do know is that we need to input a mesh. Double click to make a mesh parameter, right click, set one mesh, and we'll just select that mesh. Now we can plug this into our M input. And then we also know that we need to eventually feed in points. So we can just go ahead and do that now. So right click, change the name to points, and then create a point parameter input. Now, for now, I'm not going to set this, so we'll just leave those null for now. Now we can double click into the GH Python component and get started. So the first thing, as always, is going to be to import all of our libraries. So import Rhino script syntax as RS, import script context as SC, and import Rhino. And we're going to make sure that our script context document equals our GH document. And now we're going to set up the basic structure for this component. So the two things that we need for a mesh crawler setup is going to be the actual crawler, which is going to start at a point and then basically draw a kind of trail or movement path across the mesh surface. So moving from vertex to the next vertex based on certain movement criteria. But we need a mesh for it to crawl on, and then we need the actual crawler. And in this case, we're going to build both with classes. So first one is mesh to crawl. The one is crawler to move on. So I'm going to start by naming a class mesh map. We could name it anything, but I don't want to use just mesh, as this may get confusing when we're referring to the actual mesh versus the class. So I'll call it mesh map. Start our constructor function. This is going to be similar to the Langton's ant setup, where this is essentially a 3D space or territory for our crawler to operate on. So similar to Langton's ant, we need to feed it the mesh ID, and we'll have a property self.id equals that mesh ID. And now we're going to need self.vertexes equals rs.mesh vertices, and then we'll just feed in that ID equals rs.mesh vertex normals. Again, feed in that ID. One difference in this setup is that because we have a complex 3D geometry, we could just use the vertex normals, but it's actually going to be more efficient to use something called topology vertices. So basically in a mesh, you have all of these vertices that are connected by these edges, making up faces in between those connections. So faces containing a list of vertices, and each of those vertices are connected by edges. So we can actually navigate across this mesh, not just through the vertex ordering, which doesn't necessarily relate to the actual connections between vertexes. So it makes more sense to work with the properties that do relate to how you would actually move across the surface. So working with a topology vertex list actually allows us to find the connected vertices to this vertex. So this one, this one, this one, and this one. And we can then make a decision about which one we want to move to. So in a way, it kind of gives us a discrete operative space. So we only have those connected vertices to choose from, which limits the number of things to sift through when we're making movement decisions. So in order to use these, we just are going to make additional properties in this class. So self.t vertexes for topology vertexes. In this case, we're going to use the Rhino common libraries. So there's documentation online for this, but you can actually visualize what we're looking at by typing rhino.geometry.mesh. So this is accessing a mesh class, and then if we type another dot, we can access methods within that class. So one of these methods is actually to extract the topology vertex list. So if we just type topology vertices, this will give us the topology vertex list. So now I mentioned this rhino.geometry.mesh is a mesh class. So what we can actually do is feed in our mesh class, not the GUID of the mesh, but it's the actual instance of this mesh. So we can make a new property called self.mesh, set this equal to rs.coerce mesh, and this will convert this GUID of the mesh to the actual mesh class. So we're going to feed ID, and then we can now replace this rhino.geometry.mesh with our self.mesh. And now from our self.mesh, we can use the method topology vertices to extract the list topology vertexes. Okay, so we can leave that class there for now, and we'll come back to it later on. But before we move on to the crawler, we're going to just instantiate that by saying my mesh map equals mesh map, and then we want to make sure we're feeding in our mesh input. Now, the next thing to do is to build our crawler class. So class crawler, and we're going to build our constructor function. And in this case, again, similar to Langton's and, it's going to take as an input a position. Now, we don't actually need self.vec because in this case, we're going to just select which vertex based on certain criteria is going to be the most optimal. So we know, though, that we will need a reference to which vertex we are on. So we can call this self.index. We're just going to set this to rs.pointArray. And what we want to feed in here is actually my mesh map. And then we're going to use the topology vertex. So we'll use our topology vertex indices there. So my mesh map dot t underscore ptx s. And then we're going to feed in our self.pos. So this will give us the first index value from our topology vertex indices closest to our initial self.pos, which is going to be our input points. And now, before we finish this class, we know that this crawler class is going to require some type of run or movement function. So we're just going to say move, feed in self, and for now we can just say pass. Okay, now if we come down to the bottom, we can say my crawler equals crawler, and it needs our pos, which is actually going to be rs.point coordinates of a point. And similar to Langton's ant, if we have multiple point inputs, which I'll just go ahead and set those now. So right click, set multiple, and just click a few points on our mesh. And then we want to right click on points and change it to list access. So now it's just running this component one time for that entire list and feeding all 4 of those values in at the same time. But point right now is not defined. So what we want to do is cycle through those points. So for point in points. And now we're instantiating my crawler for each point in the list points. When we instantiate these, we want to append these to a global list. So we can make a list. And then at the top, make that a blank list that we can append to. So that's going to house each instance of the class crawler. So we can loop through all these points, create those instances, and then append them to our population. So now that we have this set up, we can step into our run function, and then we will be able to loop through the call for this run function and see how this is working. Okay, so the first thing we need to know is we know our position, we know our index we know our vertex index relative to our base mesh. So what we want to do is somehow use these topology vertices to find the connected vertices, cycle through each one of those, and then find our best option. In this case, our first input criteria that we're going to evaluate is going to be just a gravitational criteria. So which point that we are connected to is the lowest, and move to the lowest. So this is a kind of water flow based logic. So the first thing to do is going to be to find our connected topology vertices. If we actually type self.t vertexes, so vtxs, we actually have a method here called connected topology. And this is going to take an input of an index in the topology vertex list. So our current index, which is going to be self.index. So now this is going to output all of our connected topology vertices. So we can say our neighborhood vertexes, so n underscore vertexes equals all of our connected topology vertexes. Now we just want to loop through those. So for n vertex in n underscore vertexes. And we just want to check which of these has the lowest z value. We could say lowest vertex equals, and then let's just say 0, 0, and then we can make this a high z value so that we know that none of our vertexes are going to be higher than this original lowest vertex value. That way we know that it will be overridden by our first vertex, which should be lower than that value. So we'll say for vertex in vertexes, if n underscore vertex dot z is less than lowest vertex dot z, which in this case we hope that it's lower than that value, which it definitely is. So if it's lower, then we need to do 2 things. We need to say that the lowest vertex is now our current vertex that we're cycling through in the neighborhood. So lowest vertex now equals that. We want to update our position. So our self.pos is now going to equal our lowest vertex. So self.pos equals lowest vertex, and our self.index is going to equal whatever index that was. So we actually need to create a variable lowest index as well. Say lowest index equals the index of this vertex. If we actually read the documentation on connected topology vertices, we'll notice that it's not giving us the actual vertex, so the actual point position, but it's giving us a list of indices that are connected to our current index. So right now we actually have lowest vertex being set to an index, and we also are calling the z property of an index value, so an integer, and not an actual vertex. So what we need to do is use this self.topology vertex list, and then use our n underscore vtx value as an index for this list. And we can copy this, paste it in here as well. So we're actually setting that lowest vertex to the actual vertex and not just the index. And then we can set our lowest index equal to our actual index value. Now we can start our lowest index equal to, because we're not actually evaluating that, we're just setting it whenever we get our lowest index value. And then we can say self.index equals lowest index. Now if we go to the bottom, we can cycle through for I in range to 10. And we want to call our run move function for the entire population. So we need to cycle through now each item or crawler, but in this case, just for ease of use, I'm going to say for item in population, and we're just going to call item.runMove, and now it should run. And if we want to check this now, we can just print our self.pause, and you should see that updating. So hit test. So we actually have here self.topology vertices. We want to make sure that that is still my mesh map, since it's not actually in the crawler class, it's in the mesh map class. So let's just change those. Now the rest of that should be good. Let's change this to a point. Okay, so we can now see that each of these are updating. So it looks like it's working, but we want to actually have an option to render this out so that we can see the curves being drawn out across the mesh. So we just need to make a render function. And in our render function, we're going to just directly return our curves. And we're going to say rs.add interp to feed in here a set of trail points. So we can say self.trail_points, but we don't actually have this property list in our crawler class. So we need to go up to the init, say trail points equals the blank list. And then at the end of our run move, we need to append to that list our new self.pause. And we can also do this in the actual init, so it includes our starting position as well. So now we're not actually calling this render function yet. If we go down to the bottom of the script, we can say for item in population. So for each instance of the class crawler, we are going to call item.render. And now to actually output this so that we can visualize it in Grasshopper, we can just right click and change this output parameter to t, set t equal to a blank list, and then we can just directly append our output interpolated curve to that t list. So if we hit test now, okay, so it's having an issue converting a 0.3f to a 0.3d. So we can likely fix this by just appending here rs.course. So now if we hide this mesh, this one as well, we can see that those points are now drawing trails across the mesh, and it should just be following the connected vertex that is lowest, which it does seem to be. If we increase this to maybe 80, then we can draw out larger trails. We can even add another conditional statement here, because we see that it's kind of pooling here and it's even going back and forth between those two. So to prevent that, we can add a conditional to only move if it's above a certain value. So once it gets down to the bottom, it won't call the run move function anymore. So if item.pause, which is our position of that particular crawler, is less than, let's say, 10, it's greater than 10, because we only want to move it if it's actually greater than that value. If it's less than, we don't need to call the run function. Now if we hit, not that the point is, but we actually need the z coordinate, so .z, the z property value of that position. Okay, so that seems to be working now. So it's drawing out these curves. If we hide this again, you can see it's drawing those out and tracing each of the edges or the connected topology vertices, and selecting whichever one is the lowest in those. We can add a bit of functionality to this script though. So two things that we're going to add are looking at geometric properties so that we don't just have to rely on a kind of gravitational flow, but instead we could trace out curvature on the mesh. And then the second thing is if we wanted to, let's say we wanted to use these curves to trace out fabrication paths, we can see that these two start to kind of connect in there, but there may not be enough coverage with just these 4 points that we've input. So we may want to give the kind of ability to the crawler to determine whether there are neighbors close to it, and if there aren't, to actually duplicate or branch into multiple new crawlers, and then send those out as well so that we get a little bit more coverage from these. So the first thing we can look at is actually updating our mesh map function. And what we're going to do is add a couple geometric property evaluation functions. So the first of these is going to be self.curvatures, but this is going to be curvatures based on the topology vertex list. So we're going to just say t curvatures for topology curvatures. And we can set this equal to a blank list. Then we can also do t underscore inclinations, set this equal to a blank list as well. And then we just need to create functions to actually get those properties. So def curvatures and self, and we need def get feed in self. And then in order to actually check whether this is working or not, we want a render function now here as well. So def render, and then feed in self there too. So if we just preview this mesh again, or maybe even unhide the one inside of Rhino, and then I'll just minimize this script for now. So if we look at each one of these faces on this mesh, we can see that there are vertexes at the corners of each of the faces. But one of the properties that we're not actually seeing, but it does exist inside of the mesh, is the face normal. So in the center of this face, you can actually draw a normal. So we use this in the Langton's ant example. So this normal is the perpendicular direction to this face. So it's a vector pointing away from this face perpendicular to it. Now, these normals also actually exist per vertex on the mesh. So you can imagine that if this face is maybe pointing slightly more in, then maybe this vertex here has some kind of average between those two face normals. So we're already setting this as a parameter in the mesh map class, but we now want to actually compare the angle between each of the connected normals and our current vertex. So this is going to look like cycling through each of these normals, drawing out their vectors, placing them in space, and then calculating this angle in between them. And then we're going to just average all of those connected vectors to get the curvature value of this vertex. So we have our normals already there. What we want to do is say for the vertex vertexes, so cycle through each topology vertex in the list self.t vertexes. And now what we need to do is get the connected topology vertices. So this is going to be this exact same expression we used in the run. So if we just copy this up here, so all neighboring vertexes, and instead of self.index, we can just use the index value for this loop. So we're going to change this to for I in enumerate, so I comma in enumerate, and now we can use our I as the index value there. Now for each one of these connected vertices in this list, we want to compare its angle with our current one, and then average those out to get the curvature value. So for n ptx in n ptx's, angle equals rs dot angle. We want the vector angle of our two normals, the current vertex position and the normals of the connected vertex n underscore vertex. So in order to get this, we don't want our connection to the topology vertices, but we actually need to refer to this normals list, which just uses our mesh vertex list. To get this, we need to say v underscore index and then equals, And we're just going to grab our self.tBGXS, so topology vertex list, and then inside of this is actually a method called mesh vertex indices, and we just need to feed in here our index value, and it will give us the indices in the mesh vertex list, which is also the same order as our normals list. So for v index, we're going to feed in I, and then for neighbor index, we can feed in n_btx. So this gives us the vertex index and the neighbor index relative to our vertex list, not our topology vertex list. And the next thing we want is our v normal and our n normal. And we can set our v normal equal to self.normals and use our v index. So open brackets, close brackets. Then we're going to copy this line and just use our n index on this next one. Then we just want to take the vector angle, which takes two vector inputs, and this will give us the angle output. Since we don't just want the angle of one of these comparisons, we actually want the average of all of our neighboring vertexes. We can create this average by making a variable curvature, set this equal to 0, then we can add, so curvature plus equals our vector angle, and this is going to add all of the vector angles up. So then to get the average, we just need to tab out, say curvature, and then we can say divide equals, and we want it to be the length of our neighboring vertexes. So if this should kind of look familiar, but basically an averaging is an addition of all values divided by the number of values that you've added. So let's say we had a list of 10 items. We would add up all 10 items and divide them by 10. So curvature, which we've added up all of our vector angles and then divided by the number of vector angles we've added. And now we just want to remap this value because these are going to range from 0 to 180. So if I just paste in here, we can take a look at a mathematical remapping equation. So I guess what we don't see here is new value equals this equation, where we use the min of D1 and D2 and the max of D1 and D2, and then the current value to remap our current value from one domain to the next. So this is similar to remap value or remap number inside of Grasshopper. So if we just go in and fill in each item in this equation, then we can say curvature, so the new curvature equals, and then our minimum in the second domain, we want to remap this from 0 to 1. So that minimum is going to be 0, and then plus our current value, so that is curvature, and then minus our minimum in D1, which is 0, and then times our maximum in D2, so that's 1, our minimum in D2, that's 0, and then we have our maximum in D1, which is 180, minus our minimum in D1, which is 0. So if we just clean this up a bit, we can remove that, remove this, that's just times 1, so remove that, and remove this, so we get curvature divided by 180. And now we're just going to append that result to our list of all of our topology curvatures. So topology curvatures dot append curvature. Then we just need to call this function into the class. So we want to run it at the init, so we're going to just run it here, self.get curvatures on there. And then if we print underneath here self.t curvatures, we should be able to see that this runs and remaps. This one is self, not my mesh map. So hit test. Okay. Another thing is that mesh vertex indices actually outputs an array of all mesh vertex indices. And in this case, we just care about the first item in that array. So if we update that, now we have a list ranging from 0 to 1 of curvature values. Now, if we want to render that, we can go to our render function. So in our render function, what we want to do is pass in some vertex list. And then we're actually going to call this below our instantiation of this class. So we can just say m equals, and then my mesh here. And then we need to pass in some vertex list. So in this case, we're going to pass in our t curvatures. So we can copy that, paste it inside this call. And then it's not self because we're outside of the class. So instead we need my mesh map. Okay, now we can go into the render function and build this function. So the first thing we need is a list of colors. And we could make this a blank list, or we could say colors none and make it the length of self.vertexes, because we know we're going to need one color per each vertex. Now we can say for I item or vertex in self.vertexes. And what we want to do is basically use this list to get the range from 0 to 1 of our curvature values, remap that from 0 to 255, which is just going to mean multiplying that value by 255. But right now we're cycling through our indices or items in the list of vertexes, but we're feeding in a topology vertex list. So what we can do is actually say TV underscore index, so our topology vertex index equals, and then we can feed in our topology vertex list, so self.tvtx. And inside of here is a method called topology vertex index. And this is going to take as an input the index of a mesh vertex in the mesh vertex list. And it will give us the topology index related to that. So we're just going to feed in I there, and we'll get the topology index related to that mesh index value, mesh vertex index value. And now the next thing we're going to do is create a color. So we can say colors I equals rs.create color. And now we need 3 values, so R, G, and B. And those are going to correspond to our vertex list at that index, so our curvature value at that index. And that's a range from 0 to 1. So we can just multiply that by 255, and that will give us a range from 0 to 255. And we want to use that value for our R, G, and B. So now we've overwritten the colors list. Now we just need to color the mesh. So rs.mesh vertex colors, which is going to take a mesh ID, so self.id, and then colors. Now if we just return this, we can say return self.id. And when we go down to this call, we can see that our call of that function is going to return that mesh.id and output into M. So we can add that M output into our component, and now we can hit test. So we've multiplied it by self.vertexes up here at the top. So if we want to make a list of none values, we want to do it for the length of that list. So I just forgot to add length of those self.vertices there. Now if we hit test, and then for this for I in range, we need to clarify that this is enumerate. So for I and enumerate self.vertexes so that we can get both the index and the vertex value, which we actually don't need. So we could just also say for I in range length vertexes. And now we can see it's previewing our curvature values. So in our higher curvature areas, we're getting white values, and then in our low curvature areas, we get black color values. So if we open this back up and then go to our get inclinations function, what we want to do here is cycle through our list of topology vertexes. So for itvtx in self.txs. And for each vertex in this list, we want to find the normal and then unitize that so that we essentially make each of the vector components add up to a total magnitude of 1. And effectively what this does, I'll just draw this briefly here. If we had a normal that's pointing here, it has let's say, x some y component and then a z component vertical. So that might be difficult to see there, but 3 components. Maybe I'll do those in different colors. So an x, a y, and then a z that all add up to that vector. So if we know that each of those components added together equals 1, then we know that if it is pointing straight up, that z vector would equal, or that z component equals 1. And same thing for each of the other ones. So in inclinations, we only care about a normal's relation to the horizontal axis. So we can do this by actually finding the normal and just unitizing it and seeing how close this value is, this z value is to 1. If it equals 1, then we know that it is 90 degrees from the horizontal, and anywhere else it would be slightly closer to the horizontal, and if it equals 0, then it is horizontal. So this is an easy way to find inclination angles. So first thing we want to do is get our vertex index from our topology vertex index. So the index equals self.t_btxs, and then we need our mesh vertex indices, and we can feed in our index value of our current topology vertex. And then we need to just take that first item because it gives us an array output. And now we can say normal equals, or v normal equals our self.normals list, our vertex index, and we can say normal rs.vector unitize, and then this takes an input vector, so v normal. And now for this particular purpose, we don't actually care if a normal is pointed up in the z-axis or down in the z-axis, or in the positive or negative x or y direction. So we just care about the absolute value of its z vector component. So what we can say is v normal equals, or actually equals ABS, so absolute value, normal dot z. So now this should give us an inclination value of 0 when it is horizontal, and when it is pointed directly up in the z-axis, then it should give us an inclination value of 1. So we can append that value to our topology inclinations, and then we can call that function get. And now to test this, if we go all the way down to the bottom here, because we've made our render function actually take an input vertex list, it doesn't have to be that curvature list. We can actually just change this to t inclinations, and this will render out our inclination list. Okay, so it's wanting a, again, I've forgotten an enumerate here, so self.vertexes. Now we can hit test. So we can see that we're starting to get gray values where the normal is slightly on the diagonal. Where the normal is perfectly horizontal, we're getting these black values. And then where the normal is perfectly vertical, we are getting these white color values.